large magnet because of these nanoparticles. So they are very interesting for what we call micrototal analytical systems. So examples of these are DNA arrays, very rapid microfluidic chemical assay devices. So these are very, very interesting for them because you can use these particles for separation and you can also use them to enhance mixing, and we'll talk about some of these applications. They are interesting because these particles work at a small length scale. I told you about the action at a distance and the efficacy of magnetic fields to move things at small length scale. They have that small size, and they also have a very small magnetic response. In fact, these microparticles can be steered very rapidly. They don't suffer through some of the sort of magnetic saturation limitations. They have magnetic saturation limitations, but they're not as drastic as for magnetic nanoparticles. So the challenges of microfluidics are that if you want mixing, it's got very low Reynolds numbers flow, and so the strategies are active mixing or passive mixing. So generally, when you look at the most active mixing devices, like ultrasonic, acoustic, bubble-induced, electrokinetic, they are invasive to the microfluidic architecture. You now have to have a microfluidic architecture, and you have to have a fairly large power supply to maintain the power to these invasive techniques. The magnetic technique, on the other hand, is non-invasive. You just put it in magnetic microspheres, but the magnet is not on the device per se, it can be anywhere else, and you can tune it. Again, you know, I don't want to sell snake oil. It's not the perfect solution for every application. But if some of you are in the microfluidics field, and if you're looking at a particular application where mixing is challenging, think about this. So you can also use magnetic. Other challenges are that you can either use electrical fields or you can use magnetic fields in microfluidics. When you use electric fields, these electric fields can be invasive to biological organisms. Anyone who's touched a live wire knows that a high electrostatic potential can give you quite a shock and sort of be somewhat detrimental to your health. Now, the magnetophoretic devices are essentially biological. That's another example of why they can be used. Let me give you an example of immunomagnetic separation. So this is a device that was developed by two students, Ashok Sinha. Ashok is now at Technical University of Darmstadt, and Anindya Dave. And Anindya is now working for GE Global at the Jack Welch Technology Center in Bangalore, in India. So essentially what they did was they made a lab-on-a-chip device where they essentially just put in magnetic microspheres, and the device has several phases. In the first phase, you put a sample fluid containing bacteria and magnetic beads together. Then you form these conjugates with bacteria and magnetic beads. And then what you do is you activate a magnet, you pull the magnetic microspheres down. Now they've got those conjugates with the bacteria on them. And then you basically wash them with some fluid for chemiluminescence. What you do is you zap them with a low-intensity laser. They give out a chemiluminescent signal, which is characteristic of a particular protein or a particular bacteria, and then you know that you've captured a particular bacteria. So you can clearly see how this might be a device that you can use for very rapid qualitative detection of diseases if there are passengers coming to airports whom you want to screen. So rather than have two sleepy-looking people who are looking at the incoming passengers with infrared devices, now how many of you have been to an airport where people have been asleep and they've been monitoring people with infrared devices? Nobody? That's only my. Have you been? No. No? Never?
Tired.
Yeah?
Very tired, but never asleep.
Okay. All right. So this is a way where you can just collect the saliva sample very quickly and in a few seconds have a quantitative analysis. So to do some of the other things that that device into its fundamentals. We had to build a particle entrapment mechanism, and then we had to essentially come up with an algorithm to track the particle trajectories. So nothing in life is simple. You do some experiments, and you have to do some theory, you have to do some computations. So these are examples of Lagrangian computations where you actually track particle trajectory so that you know that you have a high collection efficiency. So when you design the magnetic field, when you design these particle entrapment devices, you also have to design them in such a way that they must have particle trajectories that end at the magnet. So here there's a magnet over here, some of the particle trajectories end up here, the other particle trajectories don't. That means that these bacteria magnetic particle conjugates just go out of the screen and you don't collect them. So if you tune your magnetic field, maybe all those particle trajectories will come down to the magnet. All right. So like I said, you've got to understand things about the Lagrangian motion of a microsphere. You've got to write some simple equations that is the fluid drag, the magnetic force on a particle. You've got to, and that gives you an understanding of the trajectories. I'm going through this rapidly because I was told that my time will come to an end soon. So the whole idea is to increase the capture efficiency. So the idea is you develop a device to increase the capture efficiency of the device. But you've also, in the case of magnetic microspheres, remember I told you that these are no longer monopoles, these are dipoles. So two magnetic microspheres will interact with one another. So you've got to put in dipole-dipole interaction into your model. Sorry about the funky symbols. I upgraded my Mac to math type and I lost my old font, so sorry about that. So that should be a theta. But nonetheless, you've got to have interparticle interaction models, you've got to develop them. And you've got to look at the aggregation due to these interparticle interaction models. And again, the idea is to optimize the particle collection that you have in the microassay device. And ultimately, you increase the collection volume fraction. Okay, so I'm going to briefly tell you about another application. This is called lab in a droplet. So as I told you, when you put a magnetic field onto these magnetic microspheres, they tend to align along the direction of the magnetic field, which is at a slight incline here, and form chains. So this is an example of what we call self-organization, and you can harness this self-organization to do interesting things. So what are the interesting things you can do? You can self-organize these particles into rotors inside a droplet. This is a droplet which is about 500 microns, it's about half a millimeter, it's viewed under a microscope. And what you do is, you basically rotate a magnet. So you have an AC magnetic field here. So we actually have a permanent magnet that we rotate, but it's like having an AC magnetic field. And when you do that, the droplet is actually stationary, but the rotors inside the droplet are moving. So now what you can do is, if you have an assay to do, if you want mixing, then you can do mixing much more rapidly than you might otherwise. So to understand this, when you rotate the rotor, you've got to rotate it at such a speed that it doesn't buckle or it doesn't break, because there are forces here of fluid shear, there are forces here of self-organization due to the magnetic field. So that's a challenge that you have to overcome. And when you look at the mixing, so here what we do is we put a blue dye into the droplet and we rotate the rotor as I showed you earlier. And when you do that, what you find is that when you only have pure diffusion, when you have no rotation of those rotors, the mixing time is fairly long. But once you start rotating the rotor, you start to mix things very rapidly. So it's quite an interesting microfluidic application.